So I'm going to share my screen so we can get started. And then this one. Here we go. Display settings. Okay, so hello everyone and welcome to the Science Symposium. I'm really excited to have everyone here today on this Wednesday. So today we have Dr. Otilia, Dr. Nedaa, and Shahrzad, who will be presenting her work. And as well, we are joined by Noeen in the background. She may make an appearance today if we're lucky. And myself, my name is Ashley, and I'm the Vice Chair of the Science Symposium, which is, of course, Noeen's brainchild and work, which we're very excited to be here today. So before we get started, I would like to take a moment to just do a quick land acknowledgement and take the time to reflect on our connection to the land and thank the traditional guardians of the land that we here at SCWIST Vancouver live and work on. Vancouver is on the unceded ancestral and traditional lands of the Musqueam, the Tsleil-Waututh, the Sechelt, the Squamish, and the indigenous people of Turtle Island. So we are in round 2 of the Science Symposium, and we are in the category of physical science and particle physics. And we have our third presenter in this category. So before we get started, I would like to go over a few housekeeping rules. As you may have heard, that this event will be recorded and will be put up on YouTube at a later date. We do ask that everyone keep themselves muted when you are not speaking, and that the chat box will be monitored because we will have an opportunity for an audience question and answer session after the judges panel discussion. So please, if you have any questions during the presentation, drop them in that chat box and I will be able to ask them after the presentation. Before we get started, the Science Symposium also would not be possible without the help of our sponsors. We have a couple of really amazing sponsors who have helped bring this to life. One of them is Northeastern University. They have a 95 employment rate for biotechnology. So if you're interested in that, please check them out. Another is Admire Bioinnovations. If you want to polish your skills in business or science, check out their programs. We also have AbCellera who have come on board, and they famously discovered the antibody that neutralizes the viral variants of COVID-19. So we're very excited to have them joining us, as well as Microsoft. And you can always check out their website if you are interested in any IT internships. We also have 𝐒𝐏𝐃𝐄𝐑 Therapeutics. They provided the liquid nanoparticle delivery system, a key element of the development of Pfizer's vaccine. And we have Kruger, and they recently developed a revolutionary bio-based material with unique properties. It's called PhyOcell. And this additive will enhance the performance of your products unlike any other and can be leveraged in numerous applications, including automotive, construction, and aerospace, to name a few. So a very great lineup of sponsors today. Now today we have, as I mentioned, our 2 judges and our speaker, and I will give you each an opportunity to introduce our judges each an opportunity to introduce themselves and say a little bit about the work they do, and then Shahrzad, I'll jump over to you and you can do a quick introduction and begin your presentation. So yeah, with that I will stop sharing my screen. And Nedaa, I will jump to you if that is okay to give a quick hello.
All right. Hi, everyone. Happy to be here. So I'm a postdoctoral fellow at Harvard University. I've been there since 2018. I work on the Atlas experiment, which is based in Geneva, Switzerland. I've been part of this collaboration since 2013. I work on top-related physics, mostly rare processes like 4-tops, TTH, and so on. So yeah, good luck, Shahrzad, for today.
Thank you.
And then Dr. Otilia, I'll jump over to you.
Yes. Hello, everybody. I'm a Romanian physicist, and I'm currently working at CERN as Nedaa. And I'm living in France, so hello from France. I'm involved with high energy collider experiments, and I'm also in the Atlas experiment, but since 2011. And I studied detector performance related to charged leptons, and I also conduct searches for supersymmetry and non-standard Higgs boson. So I'm interested in any signs of new physics not predicted yet by the standard model.
Wonderful. And Shahrzad, I'll jump over to you. And please give a little introduction of yourself, and then feel free to jump into your presentation.
Hello, everyone. I am Shahrzad, and I'm a second-year PhD student at the University of Calgary. So I'm here in Calgary, and it's nice to meet you all today.
Wonderful. And then, yeah, feel free to please share your slides, and we can get started.
So do you see my screen now?
Yeah.
Nice. Okay, just let me. Okay. Okay, so may I start?
Yes, please. Thank you.
So hello again, everyone. And I am Shahrzad, and I want to talk about demonstration of a model for 𝐒𝐏𝐄𝐑 cavity quantum memory. So today I'll talk about a bit about the background of my work, and then the motivation for our work, and atomic frequency comb quantum memory and rare earth ions, and then atomic frequency comb cavity quantum memory. And then I'll talk about our theoretical model, and finally, I'll talk about the preliminary results from the model and comparison to the experiment. So for the background of my work, so as you may know, in classical information science, we have the fundamental elements are bits, where they can be either 0 or 1. But basically in quantum information science, the fundamental elements are qubits, so which are basically the quantum bits and are two-level systems. And because of the inherent property of quantum mechanics, which is a superposition of the states, a qubit can be either 0, 1, or a superposition of 0 and 1. And this makes a huge difference between classical information science and quantum information science, because we can store much more information in a qubit compared to the bit. And basically, we encode information in light, but photons can easily get lost as they travel in the optical fibers. And this brings up the concept of memory in actually quantum information science. So quantum memory is a device with an ability to map onto, store, and later retrieve the quantum state of light from matter. And also there are some performance criteria for quantum memory, and there depends on the applications that the quantum memory have. But basically, the fidelity of the quantum memory is important, and which is the similarity of the retrieved state of light to the state that we sent in to store. And then the efficiency of the quantum memory should be high, should be large enough for the particular task. And the storage time of the quantum memory, which is the time that the quantum memory is able to store the information, is important based on the particular task. And also the bandwidth of the memory should be sufficiently large to interface with different single photon sources. And also the mode capacity, which is basically the number of modes or photons that the memory can store simultaneously, is important. Again, based on the particular task. So, of course, in the future quantum information technology, quantum memories have many potential applications, but I have listed some of the main applications here. So they have applications, and actually they are one of the most important elements in long distance quantum communication, to have quantum networks. And also they are important in linear optical quantum computing, and also they can be as deterministic single photon sources. So after this background, I will talk a bit about the motivation for our work. So in today's classical network, there is a challenge of insecure communication channels and imperfect guarded data. And quantum networks guarantee secure communication because of the inherent properties of quantum mechanics. And one of its long-term applications could be the creation of a global network of quantum computers. But basically, long-distance quantum communication is limited due to unavoidable photon transmission loss in optical fibers, as I mentioned in the previous slides. And in classical information, this issue is overcome by utilizing amplifiers to periodically boost the signal along the channel. But basically, quantum information cannot be amplified or copied due to the no-cloning theorem in quantum mechanics. And this leads us to the idea of quantum repeaters, which are promising quantum alternative to play the role of optical amplifiers in future quantum networks. So basically, quantum networks make long-distance quantum communication a reality by providing entangled quantum states between distant locations. So the idea is to divide a given long distance into smaller elementary links and then create and store entanglement independently for each link and then extend it to the whole distance via entanglement swapping. And this approach is possible only if quantum memories are available. So quantum memories come into the play. As I mentioned previously, they have many applications, but in my talk, my focus would be on their applications in quantum repeaters to have long distance quantum communication. So, so far there have been several proposed protocols for implementations of quantum memories. But atomic frequency COM or AFC quantum memories are promising candidates in quantum repeater applications because of their capability to store and read out multiple temporal modes, which can enhance the performance of quantum repeaters. And also the number of temporal modes that can be stored in a sample is independent of the optical depth of the storage material, which is a big advantage compared to the other protocols. So an AFC memory consists of an inhomogeneously broadened of atoms that are engineered as periodically comb-like peaks in frequency, and this is done by frequency selective optical pumping. So a resonant pulse with the bandwidth that matches the bandwidth of the comb or that matches the bandwidth of the memory is collectively absorbed, and after absorption the collective excitation initially starts defacing, but because of the periodic structure of the comb, after time which is equal to 1/delta, the collective excitation starts being in phase again, and this leads to the echo emission or the pulse that we retrieve from the memory. So in the next slide, I briefly talk about the rare earth elements doped into solids and what makes them an interesting candidate for making an AFC memory. So rare earth elements are predominantly the lanthanide group of elements with the atomic number from 57 to 71. And basically, quantum memories need isolated systems, and rare earth elements, due to their partially filled 4F inner shell that is shielded from perturbations induced by the environment, they have long coherence times or basically narrow homogeneous broadening, as you can see here. And also when they are doped into solids, because of the non-even distribution of ions in the solid, each ion experiences a slightly different environment in the solid, and this leads to a slightly different absorption spectra for each ion when they are doped into solid, and this leads to an inhomogeneous broadening, as you can see here, for the rare earth elements when they are doped into solids. And this is exactly what we want to engineer a comb, as you can see here, and make an AFC memory. So basically, to achieve high efficiency in quantum memories, usually we need large optical depths in the material, but in practice, large optical depths is difficult to gain. So To overcome this issue, it was proposed to put the memory inside an asymmetric optical cavity so that we can strengthen the light-matter interaction. And then by applying the impedance matching condition, which implies that the reflected power of the cavity is 0, the unit efficiency can be obtained, and then efficiency is only limited by intrinsic atomic dephasing. And so far, there have been several experiments carried out based on impedance match proposal, and there have been between 12 to 20% enhancement in the storage efficiency compared to the no cavity case. So putting the memory inside the cavity enhances the efficiency of the memory, but also it creates some complexities in the measurements of comb properties. And demonstration of a model for AFC memory inside an asymmetric cavity by broadening the scope of impedance match proposal seems promising, and this is what we have tried for. So in our model, we have assumed that we have an optical cavity, which is basically two parallel reflecting mirrors with reflectivities equal to R1 and R2. And we assume that we have an AFC memory inside with the background absorption inside our cavity. And we have used the approach of all over round trips of a Fabry-Perot cavity to obtain the reflectivity of the cavity. And also we have calculated the efficiency of the memory. So I have just reported the results here. And then in our first try, we have obtained some results from the model and compared it to one of the measurements that I mentioned in this slide that is done here in Calgary. So it is 2 YAG crystal with 4 millimeter long at the cryogenic temperature, and the two ends of the crystal are reflection coated with reflectivities equal to 40% and 99%, and this results in a cavity with fineness of 7 and free spectral range of 20 gigahertz. So here you can see the level structure of the 2 YAG crystal, and here you can see the inhomogeneous broadening as I explained in the previous slides for the 2 YAG crystal for this optical transition. In the next step, we try to simulate the reflectivity of the cavity with non-comb shaped crystal, so basically the empty cavity, and on the left you can see the reflected power obtained from our model, and on the right you can see the reflected power obtained by the measurement, and as you see they are in good agreement. So basically our main goal was to extract the comb shape of the AFC memory inside the cavity. So we tried to, and we had the measurement, we had the results of the measurements, experimental measurements for reflectivity of the AFC cavity memories, and also I had calculated the reflected power of the AFC cavity quantum memory. So we tried to feed the equation to the experimental data, and obtain the comb shape or optical depths of the AFC memory inside the cavity. And here you can see the obtained fitting parameters for optical depths inside the cavity. So for the optical depths or the comb shape, I assume that is a series of Gaussian pulses with the same amplitude, spacing, and width. And then I obtained the fitting parameters for the optical depths inside the cavity, as you can see here, and simulation of the efficiency of the analyzed AFC quantum cavity quantum memory shows an efficiency of about 28%, which is in agreement with the experimental results. So in the next step, actually we were waiting for the new data to compare them with our theoretical model. So then by comparing the data to our model, we can demonstrate our model for AFC cavity quantum memory. And then we can have some predictions for the properties of the comb inside the cavity and eventually the efficiency of the memory. And so we can enhance the efficiency of the memory. So in summary, I briefly talked about the background and motivation for quantum memories, and then atomic frequency comb quantum memory and rare earth ions, and our motivation to put the atomic frequency comb quantum memory inside an asymmetric optical cavity, and then our theoretical model, and I talked briefly about some preliminary results from our model and comparison to the experiment. Thank you.
Fantastic. Thank you. Just trying to pull everyone else up again. So we will now move to our judges Q&A. So I'm just going to get everybody up there. Awesome. Fantastic. So for our judges, please feel free to go ahead with your Q&A session.
Yeah.
Right.
So,
Oh, go ahead, Otilia.
yeah. So thank you very, very much for the presentation. And the study topic is not really fitting in the particle physics session, as it is more on quantum computing, on the engineering part. But nevertheless, it's extremely interesting, and it was a good occasion for me to remember a bit what my teacher told me in faculty about quantum bits and so on.
Thank you.
And also, I read a little bit to be able to ask some not so stupid questions. So, as this is not really my expertise, and I'm not an expert on this topic, I have only naive, simple questions. So it would be awesome if you can, explain them for someone which is not on the topic. So on slide number 11, you say that slide number 11 being because now you don't share anymore.
Yeah. I should
share back?
Yeah. Just let me. Okay. Yeah.
Okay, so you explain a little bit how your experiment is, but I feel that it was a bit too fast. So
Yeah, because of the time, I was a bit.
Yes. So you need photons.
Yeah.
And with this one, you create the qubits. You have a solid, in your case, a crystal, and you fill it, dope it with some ions from rare materials.
Yeah.
How do you do your experiment with these three ingredients? And when you explain this, can you also integrate the impedance matching condition in the explanation?
Yeah. So here, okay. So basically, when we have we put the AFC memory inside. Actually, I am not the guy who actually does the experiment, but I can explain it. So when we put the memory inside the cavity, actually usually it is instead of using the mirrors, they actually put the two ends of the material reflection coated. So to actually have impedance match condition in this system, they try to going across the cavity resonances and see where they obtain the minimum reflection power. So in theory, the impedance match condition implies that you have no reflection power, because when you have no reflection power, it means that all the light has been absorbed in the memory, so inside the cavity. So basically, to achieve the impedance match condition, they try to actually going across the cavity resonance to see in the different wavelengths to see where they obtain the minimum reflection power, or basically the maximum absorption. And that is the place where actually in experiment, they have demonstrated that it is actually also in theory and experiment, both of them, they have demonstrated that is the wavelengths that when you have your comb in that wavelengths, you will have the maximum efficiency for your memory in that system. If that makes sense. Yeah.
Yeah, thank you. And why are you using dope crystals? So from what I read, not much, I confess, the dope crystals are quite new, with ions from rare crystals, of course, are quite new. So what was used before, and why did you move to this?
Mm-hmm. Actually, there are different physical systems that can be implemented for quantum memories. For implementations of quantum memories, they use atomic vapors, they use hot atomic vapors and cold atomic vapors, both of them. They use Bose-Einstein condensates, but also they use the rare earth elements doped into solids because of basically, okay, I can. because of basically, because for example, actually it depends on the protocol that you want to really, I mean, make you want to have for making your like implementation of your memory. But like for example, in AFC memory, because basically you need to have an inhomogeneous broadening of absorption spectra to engineer it as a comb to have your memory. So in the rare earth elements, when they are doped into solids, they are very good candidates because on one side they have at the cryogenic temperature, they have long coherence times, which actually is like very interesting for having memory with them. And also on the other side, because when they are doped into solid, they have this inhomogeneous broadening, and this is, I mean, large enough to have the memory. So basically, I mean, they are very interesting candidate for basically making an AFC memory. I mean, for this particular protocol, rare earth elements are the most, I mean, promising and candidates really. And all the experiments have been done by rare earth elements doped into like crystals. But basically, for example, for different rare earth elements, when they are doped into different crystals, there are some differences in the properties, and like there are some optimization, like which crystal is better or which rare earth elements is better based on like what the coherence times are, what the lifetimes are. Yeah.
Okay, thank you very much. So I saw that you already used 2 solids or crystals in your experiment, and I was wondering if you try other ones too, or you have, you know, to have more a larger spectrum for your results and understand and be able to compare them.
I see. So you mean like basically other materials, right? Other rare earth elements doped. Okay. So like basically, I mean, they are, I mean, for example, in different groups that are doing this kind of works, they usually, for example, use different kind of solids. But like, because I mean, we had the experimental data for these particular rare earth elements, like thulium YAG crystal. So I used this solid, but actually my model, I think should work for other solids as well. But basically, because like for a particular kind of material, you need a particular kind of laser, a particular kind of setup, everything should be something like that. And they had done the experiment with these particular like rare earth elements, thulium doped into crystals, so rare thulium YAG. So I have compared my results to these experiments, but like my model should work for other basically materials as well.
Okay, thank you. So if we come back to slide number 6, where you explain
this one?
Yeah. So in the experiment, what was the distance between your states A and B? I saw that in some experiments, they had up to 10 meters. So I was wondering what was in your case.
Oh, actually, because this is, this is just I had a general like explanation to say like what are the quantum repeaters and why quantum memories are like important. But basically, we have not demonstrated like a quantum repeater scheme. We had a quantum memory. So quantum memory is one of the components to have these quantum repeater schemes. But like the distance that the photon usually, these short elementary links are about 100 kilometers, not more, because more than that, the photon loss would be too much. So it is not really recommended to have it like more than that. But when you want to basically transfer your information over long distances, you should really use the concept of quantum repeaters, but they are not really, they are really future technology. That's
yeah.
Yeah, but I actually what we had, I mean, what my model is that just for the quantum memory part, not for the repeater part. So yeah.
Okay. Okay. So, and this is the main question. So it wasn't clear for me what exactly you did, but now after the discussion session, I think you just proposed the model from slide number 11, right? You used the data which was taken in experiment, and basically you tested your model.
Yeah, exactly.
Right.
Yeah, I propose. Sorry.
Please go ahead. Yes.
Yeah, just yeah. So okay, so to have a like a big picture. So for long distance quantum communication, we need one of the most promising candidates are quantum repeaters. So in quantum repeaters are really just if we want to have like a same concept in classical information, they act, I mean, they are just like play the role of classical amplifiers that we have to transfer classical information. But one of the most promising candidates are quantum repeaters to have this long distance quantum communication. So in this, I mean, in the repeater protocol, I mostly explain this slide to say like why quantum memories are important in long distance quantum communication. So in the repeater protocols, we need quantum memory to store information for some time and then retrieve it when we want to extend the entanglement over long distance. So and for the quantum memory, of course, they are like several protocols for implementations of quantum memories, but amongst all of them, like AFC memory is a very promising candidate because of because it can save, it can store like I mean, compared to the other protocols, it can store multiple temporal modes. So it means that it can store many photons or many photons simultaneously, and this will enhance the performance of the quantum repeater because it can be the rate of entanglement generation can be faster. So for the AFC memory, we then they propose that if we put it in the cavity, we can have we can have enough large efficiency, but with I mean, relatively low optical depths, because I mean, especially in the rare earth elements when they are doped into solids, I mean, large optical depths is difficult to gain in practice. And then for the AFC cavity quantum memory, actually, because of some, as I mentioned here, that, for example, they enhance the efficiency of the memory when we put it in the cavity, but there are some complexities. So I demonstrate this model for AFC memory cavity, actually, which is a more general model. So yeah, and for this model, we obtained some results and compare them to the measurements that have been done here in Calgary. But now they are, I mean, we have received some new measurements, and I want to compare my model with that measurements so that if I can demonstrate my model, we can say, okay, this is a model for AFC cavity quantum memory, and we can have some predictions for efficiency of the memory. And so based on that, we can enhance the efficiency, hopefully.
Okay, thank you. I will let also Neda ask some questions. I think I took a bit too much time.
Yeah, thanks a lot for this presentation. I definitely learned a lot of new stuff to me. So yeah, I perhaps have a few basic questions. If you go back to slide 7, I believe you've mentioned
here.
Right. So here you mentioned that the capability to store and read out multiple temporal modes. When you say multiple, I mean, is there a limit of how many temporal modes can be processed together?
Yeah, for example, in the AFC memory, it has been demonstrated like experimentally that about 1,000 temporal modes can be stored simultaneously in the AFC memory.
Mm-hmm.
Yeah.
And is this something that can be improved on or even needed to improve on, you think? Or is this already too good?
Oh, I see. So I guess like it depends on like what is the what is the rate that we want our quantum repeater, like the entanglement generation work. I mean, it's good, but honestly, I'm not sure if it is good enough. I don't think that it's good enough. I think they should develop it like more. But I think for now, it is good enough. I mean, for now, it is very promising because compared to the other quantum memory protocols, I mean, it's really a good result to have to store like 1,000 temporal modes at the same time for the quantum repeater applications. Of course, for the other applications of the quantum memory, I mean, we should see like what is the most important like performance criteria and what are the performance criteria that we really want to, for example, our memory have. But like for these repeater applications, it is very promising for AFC to see that like about 1,000 temporal modes. But also it is not, I mean, the only important things. I mean, and this is the challenge of really, I mean, this is the reason that we have not like a quantum memory, I mean, like in that we can use now, because I mean, they have demonstrated quantum memories, like one of them has like, it can store 1,000 temporal modes, the other can like, I don't know, the efficiency is very high, very large, or like the storage time is very large. But the challenge for quantum memory now is that if you can have all these performance criteria here, or at least based on, I mean, based on what, I mean, what is the, like the particular use that you have in mind for your quantum memory. If they have like that, what you need for that particular use at the same, I mean, in the same system, because for example, they have a system with a good efficiency, they have a system with a good bandwidth, they have a system with good like storage time. But now the challenge is if you can have all these important performance criteria in one system to say, okay, this is a quantum memory that, and it is good enough that I can use it like in quantum repeater.
Okay.
Yeah, the challenge.
Yeah, I mean, I think my second question is that on actually this slide. So here you've mentioned the various things that one would want to achieve or improve on, and now the hope is to have a system that would have the best out of all of these.
Yeah.
So if we were to have such a system, do you happen to know which of these elements would be the most challenging to improve on, or are they equally difficult? Or
I guess like the fidelity is important, and I know that, for example, because of some decoherence in the system, it is a bit challenging. But like and like the bandwidth, because because basically at the end we expect that quantum memory is able to interface with like single photon sources, so the bandwidth should be like about like 4 or 5 gigahertz, and this is one challenge because in different system it is not really easy to, for example, have such a large bandwidth. And also like the efficiency, I mean, actually what I have read like recently, they had proposed like how can you have like a repeater, quantum repeater, even with the numbers that we have now with a quantum memory. Of course, it is not like a very like nice quantum repeater, very ideal, but like maybe to start, I mean, maybe another like another option is that like to start to have a quantum repeater, and I mean, they have demonstrated somehow in some groups, but like they are not really good enough now compared to the classical like amplifiers. And I mean, they are not really good enough now, but they are developing it. And yeah, the hope is that someday we can have these quantum repeaters. And yeah.
If you go back to the slide where you had the periodic table, I believe it was slide 8.
Yeah.
Yeah. So yeah, I mean, when you mention rare earth elements, how rare are these? And is there a preference to use one of the elements that you highlight in the red box? Yeah, I haven't seen a periodic table for a while, so sorry if this is a silly question.
No worries. Actually, I remember that's, I mean, actually, basically, they are the lanthanide group of elements that you can see here. And like, I mean, what I have seen, like mostly they use like the, I mean, this one, like the erbium, the thulium, like the europium, and like they have, I mean, for example, if you have erbium doped YAG, like you have, I mean, different kind of system. You can have again, like for example, for this AFC memory, one of the other challenges are like, if you want to have really an on-demand memory, meaning that you retrieve the light I mean, when you want, you need to have 3-level system in the to have this AFC memory. Actually, indeed 4-level system because you want to create the comp, but we say like a 3-level system. And like thulium YAG crystal is not a 3-level system in that point. So I mean, the other work that, for example, we can do is like how we can have, what are the challenges to have like AFC memory, like in 2-level systems, if we can have like the on-demand one, I mean. So, I mean, each of, this one. So here, and for example, like for erbium, for example, one of the interesting features that erbium has is that you can have the transition, which is because basically you can have the telecommunication wavelengths in erbium, so it is more easier. I mean, you use your telecommunication photon for transfer information, and then you use it in your memory. You don't need something like a frequency converter to convert the frequency of like the photons. Like before, because for example, the optical wavelengths differ from the like telecommunication wavelengths. So it depends. Like I mean, for different actually, but mostly I have seen the parasodium, like europium, erbium, thulium, but like I mean, each of them there have been several works on them, and they have different properties. Yeah, and actually I think really the challenge now is like how to have the optimized system, basically.
Right. Sounds good. Just perhaps a final question from my side. So on slide 14, where you demonstrate the result that you get.
Sorry.
Slide 14.
Slide.
You've mentioned you mentioned your result, right?
Yeah.
So I mean, do you think you can improve on this result, or is this as good as it can be?
Okay, well, actually, basically what we have done is that like we try to, because I mean, we had some data from the measurements of this 𝐒𝐏𝐃 cavity quantum memory, and what we have tried for is we try to like see if our model like is compatible with the results that we see, and if they are in agreement or not. So like I mean, the results that I have here, I mean, they are in good agreement, because we should also think that this is theory and that is experiment. So like, of course they have, I mean, they are not always like the exact match. For example, I mean, the efficiency that they have obtained in the lab for this comb is about 20%, something. So, but they are good enough that, I mean, my effort is that to show like they are good enough, the result from the model, that we can use it to predict some measurements and some experiments. So at least, for example, before doing the experiment, you know like what you want, and you can enhance the efficiency of the memory with comparing like different elements somehow. Yeah, and
Okay.
and that is why, for example, I'm trying to like using my that is why I'm trying to using my basically model for other measurements that we have been waiting for to see.
Right. So you've mentioned you're waiting on other measurements.
Yeah.
So you expect them to be different? I mean, is the experimental setup slightly different from what you have shown in the presentation?
Oh, I see. No, basically, I think the experimental setup is the same, but the data that I have received is like that. The data that I had was like on one frequency. The comb that was created was just created in one frequency across one. But this is the different combs that are created across a cavity resonance. So there are more combs and more results. So for example, they will help me to basically compare them with our model. There are different combs with different different frequencies. So I can compare them with my model. They help to improve, strengthen my model basically.
Sure.
Yeah.
Yeah. Okay. Thanks for answering my questions.
You're very welcome.
Wonderful.
So I should stop sharing, or sorry?
Yeah, feel free to stop sharing. Thank you. Thank you so much for answering. That was a really thorough Q&A session. So great job answering all of our questions. We do just have one audience question right now, and it is, what is a memory? If you could dive a little bit more into that.
Yeah. So basically, like a memory is like the device that, even in classical, now we have some memories that we store some information in them. So a memory is something like that you can synchronize different, synchronizing device somehow. Because, for example, even in these quantum repeater applications, it is important that, for example, when you create it is a device that helps you to wait some time, to have some time to do the other stuff that you should do, and then retrieve the state that you have sent in for storage, and then do what you want to do then. Because, for example, in even in quantum repeater applications, they are, the different processes are not really, they are basically probabilistic. So that memory allows you to wait until for example, you should have a successful entanglement generation, for example. It allows you to wait until you see a successful entanglement generation, and then you retrieve the state that you have, basically. So a memory is a device that you can store information for some time and then retrieve it. The important thing, for example, for this application is that you can retrieve it when you want. So, and a quantum memory, I think in that sense is really similar somehow to a classical memory, but the difference is that it should be able to store really photons, not like a classical pulse of light. They should be able to store photons. And so, yeah, I think a quantum memory is basically a device that helps you to do this. Even, for example, in quantum computing, for example, suppose that you want to do you want to do like a calculation, and for example, you have the result of part of your calculation. So still you need a memory to store that result in, and then have the other parts of your calculation and just retrieve it when you want. Yeah, so basically I think like the memory that we have, it should be able to store some information for some time. Yeah, I hope that this answers your question.
Yeah. Oh, that's wonderful. Thank you so much. That was our only audience question. So I would like to say thank you very much to our judges for joining us today and helping with our symposium. And maybe Dr. Otilia, I'll call on you first for any closing remarks you may have.
This nice presentation. Thank you for the explanations, and good luck in the future and in the selection for this concourse.
Wonderful.
Great.
And Dr.
Yeah,
Nedaa?
it was a pleasure. Thanks a lot. Definitely learned a lot. And yeah, good luck with the next steps and finishing your PhD.
Thanks a lot. And it was a very, it was a pleasure really to be here. And thanks for your time.
Wonderful. Yeah, it was a pleasure to watch your presentation. Really, this isn't my area at all, but it's very fascinating to hear about the science that's going on. I'm just going to share my screen again quickly and do some closing remarks, and then we can wrap up. So, yeah, so we do have, I believe, 3 more Science Symposium events coming up. So if you're interested in catching any of those, you can head on over to Eventbrite and you can see all of the events there, and you can register for those as your interests guide you. And you can also head to SCWIST.ca/events, and you will find all of the events lined up there as well. The next one is happening on September 1st, and that will be focused on global warming. So if that's an interest to you, please come check it out. And lastly, if you are looking for more information on the Science Symposium, you can always head to our website and check out our catalog, and we have more information there. Now, I just want to say thank you once more to both of our judges and to our presenter. It means a lot for all of you to make the time to come here and join with us today. And with that, I will give you the rest of your afternoon back. So Shahrzad, thank you again so much
You're very
for the presentation.
welcome. Thank you.
Yeah, we'll hopefully be in touch soon.
Thank you. Have a nice day.
Yeah, you too. Bye-bye. And I will stop recording.